Yes. So first I will say a few general words about the project. Then I will present its architecture, the Barista library that is used as a compiler backend, and then, if time permits, some examples and benchmarks. So first question, why would one want to compile OCaml sources going to Java bytecodes? The first reason is to access to libraries, because as you probably know, the OCaml community is a bit smaller than the Java community, and as a consequence, it lacks bindings for such fundamental things like databases, queries, etc. Another compelling reason is multi-core programming, because the original OCaml implementation is flagged with global runtime lock, which means that at one time only one stack can execute OCaml code. It is based on the fact that the garbage collector is not parallel. And last and probably least reason is the security. In some settings, like compilation farms or web factories and so on, the fact that you run on virtual machines such as the Java one allows you to have a fine-grained security policy. So how do you achieve compilation of OCaml source to run on a Java virtual machine? Obviously, you have to compile to Java bytecode, but it's also nice to extend the typer in order to be able to manipulate the Java elements from your OCaml sources. And you should also provide a library to allow easy multi-core programming. In this talk, I will focus only on the first item. So, some about the calendar. Currently, what I will present is available as a binary preview for version 2. Previous versions that are available with sources, manual, etc. were merely a proof of concept and were indeed very slow. And I just wanted to point out that the last version, the last major version of Java, really improved things regarding performances. Most notably, it provides with so-called method handles that are akin to function pointer in C, which allows to easily implement closures. So some words about compiler architecture. The original OCaml implementation provides indeed two compilers, one targeting a custom virtual machine, and the other one providing native code compiler. That compiler starts, of course, from an file at the top. Then they share some passes over trees, parse tree, title tree, etc. Then the two compilers will follow different paths. On the left, the compiler will generate bytecode for the OCaml machine. It is pretty straightforward because, of course, the OCaml machine has been designed to run functional code. And you have far more passes to get some native code because, of course, in this case, you have to target a register-based machine and not a stack-based machine. So what the compiler, the OCaml-Java compiler does is, in fact, start where the two other compiler suites, and then have a few places to generate bytecode. Some words about how values are represented at runtime. So, in general principles, OCaml compilers are based on type erasure. They use a unique value type for all elements that are manipulated at runtime, which is pretty convenient because it ensures that it is easy to compile polymorphic code, even in the context of separate compilation. Another very important element is that, of course, OCaml is strongly and statically typed, which ensures that there will be no type confusion at runtime, which means basically that the type erasure is safe. And it also ensures that we will not try to access to an existing element. I mean, we will not try to access to the third element of pair, for example. So here I basically give a grammar of values as they are manipulated at runtime. So a value can basically be of three kinds: a long and boxed value, so a var int, a pointer to a managed block, and a pointer to an unmanaged block. In the original implementation, you can discriminate an unboxed integer value from a pointer to a block by tagging. The rightmost byte is set to 1 for long values and to 0 for pointer values. And you can discriminate a managed block from an unmanaged block by checking if it belongs to the OCaml managed by the garbage collector. Then you have different kind of managed block. In fact, only the first one is really important. The other one are just optimizations. So basically, managed block consists of a header with a tag, a size, and the size tells you how many other sorry, not blocks, how many other values your block contains. So, tagging of values allows convenient and efficient encoding, but of course you will not have tagging available in Java. So it implies that you will have to define a class hierarchy with an abstract value class, which has two children. A long value class, which is a concrete class for long var int values, and another abstract class for block values. Then again, as in the previous slide, for block value you have different possibilities that are encoded through the class hierarchy. What is very important and about data representation, it is what motivates these slides, is that probably as a first step you will want to represent a block of values as an array of values. It is the simplest representation that will come to mind when working in Java. But indeed, it will be very slow. The reason is that in Java, every time you access an element, the just-in-time compiler of the virtual machine needs to perform a high-level check, and you cannot avoid that. More precisely, the hotspot compiler of the Java virtual machine will only remove array check if he can prove that the index is in rows. However, if you recall what I said about the principle of value representation, the static and strong typing of Java ensure that if you have a pair, your code will never try to access to the third element. So basically, it means that if you use an array to encode a pair, also you are absolutely sure that you will not try to access to an invalid index, the Java virtual machine will still do array checks. So unfortunately, the only solution to get decent performances is to kind of inline your data structure. And so for there, here, you will not define it as an array of values, but as two fields, each one storing one value. So you do this for block value 2 of size 2, which is quite important because, for example, it happens to be used for list. And then you wonder which is the needed inlining to get decent performances. And the answer is quite bad because you need to get decent performances. You have to define custom classes of this kind up to 8. This is practically measured on the compiler test suite. So of course you can generate the source code mechanically, but it is still sad to see that you have to plug your code base with such thing. But again, this is the optimization that gave the biggest impact on performances. Some words about the Barista library, which is used as the backend of the compiler. It also ships as a standalone library. It allows you to represent Java class files in both high and low-level fashion. The low-level fashion is apparently mapping from the specification of Java class file, and the high-level representation takes advantage of the OCaml typing to ensure that you will not produce bad class files. Well, not important, but it also provides an assembler and assembler for the Java virtual machine. And what is quite nice indeed is that it provides automatic computation of stack maps, which means that basically you just have to produce the bytecode, and the library is in charge of all the boilerplate stuff. What is also important is how you can represent the control flow of a function. So it turns out that the easiest representation is to use a graph or neighbor graph, where nodes are labeled with a list of Java instructions. And you have edges that obviously encode the control flow, and that have different kinds. You have a classical sequence edge that is connecting to nodes. You have a choice, some choice edges that connect three nodes, one source and two destinations that are chosen according to a condition. And more generically, you have a switch node that connects one source and as many destinations as you have map, as you have elements in your switch. And also, you have a particular kind of edge that are used to represent exception numbers. So here is a very small example about methods that basically load two integer values in the top node, and then the edge underneath is labeled with a condition. So here lower or equal, and it chooses one of two blocks to execute. And as you can see, the block on the left is actually protected by an exception handler, and the protected node is linked to its handler with a dotted arrow that is labeled with the exception to be called. What is important about this representation is that it allows you to easily encode two kinds of optimization. So-called structural optimization, that is modification of the graph structure. It may be, for example, network elimination or jump or unjump simplifications. And it also permits you to encode optimizations that are only based on modification of the node, the so-called non-structural optimization, which allows you to remove redundant operations in entity operation, and also to apply some strength reduction. Yes, I have some time to show you some generated data. So on the left you have a very simple OCaml function computing the length of the list, and the resulting bytecode on the right. What is interesting about this example, as you will see, is that it provides an example of tail call recursion. So the first thing is how to compile the match construct. So basically, you just have to load the parameter, convert it to the long value, and have a condition on the resulting value. When you will have a recursive call, you will first compute the value for the first parameter here. So you just have to implement the value of hack. The value of the second parameter is done here by accessing the second element of const node. And then the encoding of the actual recursive call is done by only throwing back the computed values to local values to local index 0 and 1, and go to 0 is a jump on the start of the method. And in the other case, you just have to load the first parameter and not on it. So it kind of proves that tail call optimization can be done when targeting the Java virtual machine, as long as we are talking about direct self-recursive function. Well, I'm running a bit out of time, so I will not present this example. It is available in the paper. It only shows that numerical code is compiled as efficiently as possible. It is exactly what you would have written by hand. Okay, obviously I have to spend some time on benchmark. They are currently not that bad, I would say. What is shown is the ratio to the OCaml compiler that is producing native code. And all benchmarks are taken from language shootout. So as you can see, except from the middle example, we are between 2 or 3 times slower than native compiled code, which is not that bad. Particularly if you remember that now you can do multiple programming. On one example on this slide, the anybody example, it is actually faster than native compiled code by a few percent. So as of today, if you want to play with the implementation, it is available at this address. Currently, the source cannot be seen, but code generation is complete, so you can compile any OCaml program and run it on the Java machine with no problem. There is still some work to do about type extensions, and a lot of work to do on the parallel library. Future work, needed to get better performances will be about more aggressive unboxing, because it is what pays much, and as I have shown, you have a fundamental problem in the Java virtual machine that you do not have tiling, so everything you manipulate is allocated. So you put a great pressure on the garbage collector, and it turns out to be your major problem. Generative bytecode can obviously be done in a few weeks. What is difficult is to design runtime implementation that is efficient. And by doing unboxing, in fact, you can, in some portion of compiled code, avoid allocation and use Java primitive types. And this is where you will get the same performances. Some work should also be done on inlining, but it is mainly to give you more opportunities to do unboxing. And related to what I just said, I have to investigate the impact of garbage collector parameters on execution time, which are not required for now.
Other questions? Yes?
So, can you comment on, in your benchmarks, the percentage of the time OCaml took in the garbage collector versus the amount of time you're taking, your running code is taking in the garbage collector?
Yes.
Just to say, if you're comparing just the mutator runs, what would they look like?
Yes. I only remember rough numbers, but when it gets bad, the native OCaml compiler will spend 5% of its time on the calculator, and on Java it will be 20%. This is what hurts, basically. So this is why unboxing is so important. And this is why what I call data mining is also so important. It is not related to your collector per se, but you get the feeling that what matters is not the bytecode you generate, but the actual shape of the object you manipulate.
One more question?
Did you consider writing a OCaml bytecode interpreter in Java and then using that as a cheat platform for
yes. It was done as a first step.
Yeah. How bad was performance if you compare that?
I think it was only slightly slower than the original OCaml solution.
Okay.
but the OCaml virtual machine is itself roughly 10 times slower than native compiler.
Yeah.
Okay, thank you very much, Xavier.